Okay, thank you.
I just need to put in up the time. Okay, so that okay. So let's start with the question: what is geothermal energy? If we go to the Wikipedia, then it defines geothermal energy as the thermal energy generated and stored in the earth. That's how simple it is. Thermal energy generated and stored in the earth. Okay. If we look at another source, that's NL, so that's a source in the Netherlands where you can basically find all sorts of subsurface data that was generated from drilling and mining activities. And there, the definition of geothermal energy is the warm groundwater at greater depths in the subsurface is a sustainable source of energy in the Netherlands. The water, which is at a temperature of 45 to 120 degrees, can be exploited by pumping it out of the aquifers at depth of 1.5 to 4 kilometers. Currently, this source of heat, known as geothermal energy, is used for heating greenhouses and homes, for example, but in the future it could also be used for industrial processes and to generate electricity. Okay, so that's the Dutch situation. Now let's go back. I mean, this geothermal energy, this heat of the earth, this is something that's been known for a long time. And what I add here is this picture from this medieval, or it's actually no longer medieval, but it's an old knowledge kind of that this guy Athanasius Kircher collected. He was a church Catholic scholar who traveled the ancient world at the time, and he also went to Mount Vesuvius while it was at the brink of eruption. But he still he was lured into the crater to see firsthand what was happening down there, and from that he concluded that in the earth there was that the earth was filled with fire and with water. And this is basically, if you wish, the first kind of depiction of geothermal energy that I could find. And I like it very much. So it's from this work that he published in 1665. It's called Mundus Subterraneus. And he was actually not that bad if we think how geothermal energy works in principle. It's like what we need is we need a heat source at depth, okay? So in this image here, this is a magmatic intrusion, but we don't necessarily need a magmatic intrusion. We just need a heat source, whatever it is. So it's hot, right? And what else do we need? We need aquifers, like they are shown here. And so the water in these aquifers is heated, right? And if you have good permeability, and then the water can actually, there can be convection of the hot water, right? Of the water. And if you have like a fracture zone where the hot water can ascend, you will have some things like hot springs like this, what you have here on the left. And the water is actually recharged from the surface primarily. It's rainwater, surface water that slowly moves downward where it recharges the geothermal reservoir. That's kind of a schematic area explanation of how geothermal reservoirs work in general. If we look at a map of the world, we can actually see that there's a concentration of geothermal power plants, so where geothermal energy is used to make electricity, in certain areas. And this is primarily in areas where we also have a lot of volcanism. You can see this concentration around this area here, the Circum-Pacific area, which is called sometimes the Ring of Fire, because you have a lot of volcanoes on both sides of the Pacific. And you can see these white triangles. They are areas where we have geothermal power plants, or lots of geothermal power plants, like here in Indonesia or in New Zealand, or on the west coast of the Americas, but also in Iceland, for example, or in Kenya. These are all regions with intense volcanism. And what we see then is features like this. This is from Iceland. So where we can see that sometimes the hot water can actually come to the surface. So we know there is hot water down there. There is a geothermal reservoir that can be used for energy provision. But sometimes, it can also be used as a spa, like shown here in Japan, where not only humans enjoy the benefits of hot water. Now, if we look at the developments of geothermal energy use, then I like to refer to the cradle of modern geothermal energy. That's a small town called Ladarello in Italy, in Tuscany. It's kind of almost 2 hours south of Pisa or Florence. And what happened there is that already the ancient Romans knew to appreciate the hot water that was available in this region. So like in a neighboring town in Castelnuovo Val di Cecina, they excavated these ancient Roman baths. And this is our students during a geothermal field trip. They appreciate the geothermal features here, and you can see this is steam. This is steam coming out from fractures in the subsurface. That is actually an intensely used geothermal area there in southern Tuscany. And there you can see the sign of a geothermal power plant, relatively big one. And you can see the hot water pipelines also in the valley, and some steam coming out from the ground here in the front of the picture. Now, initially in the Middle Ages, when they discovered these, I couldn't say they discovered them, but when they actually started to use them like for industrial purposes, these hot springs, they didn't really want to generate energy, but they used them for metal processing, because these hot waters, they contain a lot of minerals. Yeah, this is not pure water. And so this is from an old mining book from Georg Agricola. Who showed, how basically they get precious materials from these geothermal fluids. And these chemicals and materials and minerals that they actually got from the precipitation of these fluids, they were, amongst others, for example, the basis of colors, like these colors that were used in the frescoes in Florence here. This is a famous example, Santa Maria del Carmine, for those of you who have a cultural interest. And so they have analyzed these colors, some of these colors of the clothes of these people, and realized that the minerals actually came directly from the hot springs nearby. The way they did this is that they basically had these what they called lagone. Lagoni are these covered outlets, basically, where they evaporated the fluids and then scraped off the minerals that were there. And because there was a very high boron concentration in Ladarello, that was the primary target of the industrial development there. They really wanted to have the boric acid, because that was a basis for glass manufacturing. So and this became a really big industry, because glass is something that everyone wanted. And at some point in time, Italy was the #1 boron exporter in the world. So and that all came from there. So it was really a big industry. And when they realized that the demand was much higher than what they could supply, they started to drill. And there was no things like a drilling technology or oil industry that knew how to drill wells, didn't exist at the time. So they were real pioneers in trying to drill wells with whatever methods they could conceive at the time, because they realized if they drilled, even if it was only a few meters, the water was already much hotter, because it was already steam, which is something that made the whole process of metal or boron extraction much more efficient. And so this whole industry developed there in this town that is now called Laderello, and it's actually, the town itself is not very old because it was built by the owner of the plant, of the industrial plant, and it was a French guy called, it was a Duke of Laderel, and that's why it's called Laderello. And this is his son-in-law, the Prince Piero Ginori Conti, who was then in charge of the operations in the early 20th century, when he realized that, you could do more with the hot water than just get chemicals out of them. So what he said, okay, let's try and drive a turbine or a power plant with this steam. And so he had this first prototype in 1904. He showed that you could actually generate electricity with the steam. And with this prototype, he was able to light 5 light bulbs, and just to demonstrate that it works. So this is a photo that everyone working in geothermal energy knows. The Prince Piero Ginori Conti in 1904, showing his first prototype of a power plant. And but then the thing was really commercialized, and by 1913, the first commercial power plant was in operation in Laderello, producing electricity for the factory that was still making the boric acid for export. So basically, he used the heat plus the chemicals, and then they used this electricity to light and the factory buildings and the surrounding apartment buildings for the workers. So they were probably some of the first workers' dwellings that had electricity in Europe, because they just generated it directly from the heat. By now, many countries in the world generate electricity from geothermal. So I tried to update what the state was in 2020 in terms of megawatt installed capacity. And you can see that these countries around the Pacific, like the US, that's primarily the west coast of the US, California and Nevada, have the highest installation worldwide. But then also countries like Mexico and the Central American countries. Also Chile is starting now to produce electricity. It's not on the map yet. And then here in around the Pacific on the Asian side, it's the Philippines, Japan, Indonesia, New Zealand, countries with very high installed capacity of geothermal power. If we look at the top countries in terms of installed capacity for electricity, we see here it's the US, Indonesia, the Philippines, Turkey, New Zealand. Those are the ones that have more than 1 gigawatt installed capacity. And then Mexico, Italy, Kenya, Iceland, and Japan are the ones to follow up. And so those are all countries where geothermal energy plays a major role in the energy supply. Now, if we look where all this heat comes from, right, we can see that there is, this is a picture of the Earth, and that's about as much geology as you'll see today. And the Earth is composed of basically in several layers. And so we have the outer part, the outermost part is the crust, which is very thin. It's like tens of kilometers. Then we have the outer and the upper and the lower mantle, and the inner and the outer core. And in the core, the temperatures are around 5,000 to 6,000 degrees Celsius at these very high pressures. This heat basically is residual heat that comes from planet formation. And of course, the heat kind of migrates upwards. And the crust more or less protects us from a very hot planet, so that we can actually live on the surface. But also in the crust itself, there is heat generation, because there are radioactive minerals in these rocks, sometimes in the crustal rocks, and the decay of these radioactive isotopes of uranium, etc., also leads to a heat generation. So that generally we know there is a temperature increase in the crust in the topmost part of 3 degrees per 100 meters on average. Right, in places where we have volcanoes, it's more, in other places less, but on average, this is what it is, and that's also what it is roughly in the Netherlands. So no matter where we are, we have a temperature increase going deeper, right? What this means is that 0.1% of the energy that's stored in the Earth's crust could satisfy the world energy consumption for 10,000 years, based on today's numbers. But as I said, the heat is not evenly distributed. You already saw on the map of the world that, highest temperatures are obviously around the Pacific or in volcanic areas. So that's where they have power plants, because they don't have to drill so deep to get to high temperatures. But even in other parts of the world, there is still heat that could be used commercially and economically. This is a map of shows temperatures at 2,000 meter depth from places where these data were available in Europe, and you can see that this in places like here, Italy, Tuscany, where Ladarello is, or Western Turkey, or Iceland, temperatures are very high. They are sometimes above 200 degrees at 2 kilometer depth. So the gradient is more than 100 degrees per kilometer, not just 30. And then we have places like here, Central Europe, where where we have like 60, 70 degrees at 2 kilometers depth, or here the Netherlands or the Western Germany, where it's a little higher, maybe 80 to 90 degrees. Now this means, we cannot just use the hot steam to make electricity, but we have all sorts of other things that we can do with the heat. Like we have what we call shallow geothermal energy, where you can have heat exchangers and heat pumps to use for residential heating, or and then we can also store heat. Like if you have excess heat from heating buildings, we can store that at depth and at a certain depth, and then recover it again in the winter when we need it. And we can what we call use what's sometimes called direct use. So the heat is high enough that it can be used directly for heating, for example, greenhouses or buildings in general. And we can go very deep, where we have very high temperatures that we can actually generate electricity, or we could even have industrial heat for industries that need high temperature processes. So I will not talk much about shallow geothermal. My focus will be on deep geothermal. Just give you a quick idea, shallow geothermal works very often with heat pumps, and that's probably what most of you may have seen before, because many houses have heat pumps. And these heat pumps use the kind of relatively stable temperature in the subsurface at depths of maybe 100, 200 meters. And then they use like a fluid that is heated up in the subsurface to maybe the stable temperature down there is 10 degrees or something. If it's an antifreeze, 10 degrees is okay, but now the heat pump compresses it, and the house is heated. When it's cooled down to maybe 0 or something, goes down there, is heated up to 10 degrees, etc. So basically that's the energy gain that you have from these kind of very shallow systems. Or you have hot enough water for a geothermal spa, for example. Okay, that maybe this is the wrong example here, because this actually is the hot water is from the cooling system of a geothermal power plant, because it's in Iceland. But you can also have direct thermal waters, of course, for spas. Or what they do in Iceland as well is, because they have so much heat there, that they actually have floor heating for the streets to de-ice them, or to keep them ice-free in the winter. Or here in the Netherlands, and I like this. This is a greenhouse. It's close to Pijnacker, or actually in Pijnacker. We have 2 geothermal operators in Pijnacker. It's Amerlaan and Douwstein, who run greenhouses basically to grow plants. And this is where we actually went for field trips. We sometimes do that with our students, that we go and visit those geothermal the greenhouses, and the owners explain to us how they use the geothermal energy for their greenhouses. Now, if we look at in Europe, the location and the size of deep geothermal heating and cooling systems, you can see they are quite spread. I wouldn't say all over, but quite spread in many places. And you can see that in the Netherlands, we have quite a few, but also here, like, for example, in Bavaria and Germany, or here a famous one is around Paris. And of course, Italy and Turkey, the places that also have power plants, they also have geothermal heating. Like an example I like a lot because it's been running for like, I don't know, almost 50 years now. It's district heating systems in the Paris Basin, where they heat more than 200,000 apartment buildings, no, apartments, sorry, not apartment buildings, in the suburbs of Paris. And this has been going on since the first oil crisis in the early 70s. And most people don't even know that it's geothermal heat they have. It's just been running reliably for decades. And if you look at the Netherlands, you know, you can see that there's also a lot of development started. It started in 2007 with the initiative of a greenhouse owner who wanted to have, let's say, renewable heat, or also maybe cheaper heat than what, because he spent a lot of money on heating his greenhouses with natural gas. And so what you can see is here on the right, this is a map of the Netherlands with the temperatures at 2,000 meter depth. You can see that it's not uniform throughout the Netherlands. There are areas where it's warmer, like here. It's due to the geology, of course, or here in the north. And you can see that there are, on the left map, you can see there are these licenses, geothermal licenses that have been granted to many potential developers. So the green areas are geothermal exploration licenses, and the kind of magenta colored there ones where they already have production licenses. So we'll just zoom in here and look at this, the Delft area, or the, let's say, South Holland. And you can see that there are a lot of individual licenses here in the Westland, where there's also, of course, a lot of greenhouse industry. So it's primarily greenhouses, but not only. Because we also have a district heating system in Den Haag, which is now developing a geothermal component. And you can see here on these pictures that this really is in the middle of the town, right? So you can see the traffic around it and residential buildings, etc. And here is the location where they're drilling. And I like this picture because what it shows is one of the big advantages of geothermal heating or geothermal energy over other energy sources. Yeah, you can see this is, so they are planning to have 7 megawatts thermal with a temperature of 76 degrees, also from about 2 kilometer depth. And what this shows you, you know, and that you have this very densely populated and built urban environment, and they can still develop a district heating system there from have a source there. It's because one of the big advantages of geothermal energy that it has a small surface footprint. So a geothermal power plant of that size, I took here 10 megawatts, but because it doesn't really make a difference if it's 7 or 10, with an electricity provision of this, let's say for 64,000 people, that's an example from southern Germany, would occupy such a an area of maximum 2 football fields, right? If you want to have the same amount of electricity from a PV power plant in our climatic regions, this is the surface area that you would need. And so that's one of the big advantages. Another big advantage, of course, is that geothermal heat can provide baseload energy. So geothermal has on average 8,000 hours that it is available. That is actually it has more, it's available 24/7, but 8,000 is an average, we say, because sometimes you have downtimes for maintenance purposes, and sometimes the demand is simply not there. But compare that to other renewables, and you can see what the big difference is. So photovoltaics, if you want to have the same amount of energy produced from photovoltaics, you need 8 times the installed capacity, right? That's what this means. So 1 megawatt geothermal corresponds to 8 megawatt photovoltaics in terms of produced electricity or heat at the end of the day. Okay, photovoltaics is not used for heat. But in general. This is just to give you an impression. That's one of the big other big advantages of geothermal energy. And of course, we are not just, we are TU Delft. We are also doing research in this field, and we are also very proud that we've had students who took the initiative in 2007 and said, hey, we also want to have a geothermal well on campus. We want to drill our own well. And we think this is great. And this has been, pursued on and off. And now we are actually at the point where we are drilling. The university has announced they will already. It was announced 2019 that they were ready to drill. It's been taking a bit longer because there are all sorts of legal issues also with the companies who will be involved doing the commercial part of the operations. But primarily, I'm telling you this because it's also going to be a research infrastructure. So at TU Delft, we are going to have a geothermal well that is used for heating the campus, plus it will be a major research infrastructure. And the way that this will be it will be drilled on campus. I'm going to show you an image in a minute. And the way it's going to be, there will be one location where both wells, the well where the hot water is produced from and the well where the cold water is re-injected to, they are both at the same location, and they are drilled to vertically to about 800 meter depth, and then they deviate so that there is a distance between the production and the injection well. So we don't immediately produce the cold water that was injected from our production well again. It has enough time to be reheated before it reaches the production well again. And so what this looks like, I mean, this is an image basically of the reservoir, from a reservoir simulation software, and it shows that this is where our two wells will be. They will drill into this location down here, and this is let's say an artist's impression of what this will look like on campus and on what will be done in these wells. You can see, so they're not going to be these holes, of course. They were just made for us so that we can see where the wells will be. And you can see this is the heat, the heating center on campus, where the wells will actually deliver the hot water to. And these are the pipelines on campus here. Oh, no. And you can see that these wells will go, the hot water production well will go here, and the other one, the cold one, will be here. And if you look at these kind of enlarged images of the wells themselves, you can see that there's all sorts of equipment that will be installed there. And primarily, what I would like to mention is that both wells will be equipped with fiber optic cables, so that we can measure the temperature throughout the depth, the entire length of the wells. But we can also measure strain, deformation, and we can also measure acoustics. So if there's any kind of noise related to this, or any vibration that is related to the operations, this can be recorded, and that generates a lot of information of the subsurface processes. Of course, we will also retrieve cores from our wells, and we will have all sorts of seismic observation stations. So whenever there are any vibrations, any seismic shaking or whatever, that can be recorded from shallow wells that we are going to drill, also for observation of the operations. So this will be a unique research infrastructure in an operating system, and we can't wait for this to start. We hope that the first well will actually be drilled this year, and there's a lot of research projects are lined up for this. And with this, I think I've done my half-hour talk, and I'm looking forward to receiving your questions. I see there are already questions in the chat.
Well, thank you, David. That was really interesting. And yeah, I will start with the questions. I can read them for you.
Okay.
So the first question is from Tim. He's asking which different master programs focus on geothermal energy.
Actually, I'm only aware of one at TU Delft. If you're referring to TU Delft, I mean, worldwide there are of course a lot more than we have here. And at TU Delft, it's the one we have in geoscience and engineering in our department, where we focus on where we have a geoenergy track, and that geoenergy. So you can do geoenergy engineering, basically, which includes a lot of geothermal. I'm pretty sure that there are at 3ME, for example, there are also, let's say, aspects of geothermal included in, let's say, power plant, or there are also people who look into geothermal heating systems, for example, etc. But there is not let's say, a specific focus on geothermal in any of them. So they included maybe in the courses, and I honestly don't know to which degree this is done in other departments, but I know there is no class that has geothermal energy as the main focus, except in our department.
Right, thank you. So next question is from Gildo. What are the possible downsides for using geothermal energy?
Well, there are several aspects. One of the things is, of course, that drilling wells is not cheap. And if then you realize that you don't have enough, let's say, hot water for production, then it can be economically very challenging to make this, let's say, successful. Also, fiddling around with the subsurface is always challenging, and there's always a certain risk involved. I mean, you in the Netherlands, we are particularly sensitive to this since Groningen. I mean, for decades, Groningen was a safe energy supply, and we have made billions of euros by generating and using and selling the gas from there. And all of a sudden, we realized that it's actually causing seismicity. Okay, the risk in geothermal is a bit smaller because we are not extracting, so we are re-injecting as well. So there is no net volume change in the subsurface, which reduces the risk of subsidence, right? But still, it's like fiddling around with the subsurface is never, ever. It doesn't matter what purpose why you are drilling or what you're doing in the subsurface, never without risk, okay? So there could also be induced seismicity due to geothermal, and it has happened in the past as well. Just as with coal mining or with hydropower, they all, whenever you interfere with the subsurface, you run this risk, and that's also true for geothermal, of course. Another point is with geothermal that the fluids themselves, there, of course, is not drinking water quality. In most cases, this is actually a pretty disgusting brine, if you want to know the truth. So that's why it's really good that we actually produce it, cool it down, and re-inject it exactly where it came from. That's it's a good solution in my opinion, because that's where it's happy and where it's in kind of more or less in equilibrium with its environment. But if that water actually got into the drinking water supply for some reason, that wouldn't be so good. It's really not nice, not a nice fluid. Those are things, but I think that the circulation of the fluid, this is something that is pretty much, I would say, in control. I'm not aware of any major incident related to the fluid chemistry, but theoretically, I mean, it's a risk. Okay, that was a long answer. Sorry.
Yeah, thank you. It's okay. How deep would deep geothermal boring have to be to generate electricity in the Netherlands?
Well, to make this efficiently, to do this efficiently, you need, let's say, 120 or so degrees minimum. Because, to make it work, from a point of thermodynamics, you need a large enough temperature difference between the hot water and the cold re-injected water. So how much you can cool it down? That's really the key question. How much can you cool it down? And for that, you should have something like, 120 degrees, I think, would be the absolute minimum. There are places in the world where they use lower temperatures, like the The lowest one I know that is used for electricity is in Alaska, where they have something like 75 degrees or so. But that's because the ambient temperature is so low that they still have a relatively large temperature difference. But even there, I think it's half a megawatt or so electric. It's really not much. So for electricity, you really like to have higher temperatures. That's the key. Yeah.
Well,
So we could go to 4 kilometers, for example, in the Netherlands, and maybe then that was the original question, right?
Yeah. Why is geothermal energy not part of the government's climate agreement? There is a lot of resistance to mainly wind turbines on land. Is this a possible alternative to the targets for 2030?
It is. It is official part of the government's plans, but just for heating, not for electricity. Right. There is a very ambitious plan. There is a master plan geothermal, and that foresees installation of quite a bit of geothermal heating by 2030, but by 2050 they want to have something like 700 or so geothermal wells. So it's substantial.
Right. Next question: is there a connection to the new district heating system of Delft South?
We hope so. At the moment, these are negotiations, and the city of Delft, I'm pretty sure they would be happy to take the heat from the Delft campus once we have it. So these are negotiations. It would make sense because we will probably produce a lot more heat from our campus wells than the university will need. And but this is something, it's still, that's the business part. I'm in the science part, so.
Okay, next one. Do you think there are a lot of missed geothermal energy opportunities in the Netherlands?
Of missed opportunities? I think so. A lot of maybe is exaggerated, but there are opportunities, and this is because there are some regulations are still not clear enough, and that's why people are shying away. And one of the things is, for example, is related to induced seismicity, because there are places like in Groningen, people are very, very touchy about drilling new wells, which is understandable based on the experience they've had. But for me, it's a missed opportunity. And at the moment, people say, like people from industry say, stay away from gas extraction areas. It doesn't, you shouldn't do that. But we know that in lots of gas reservoirs, we have a lot of hot water as well. So I think we need to find some sort of solution. How can we use areas where we think there is a certain risk of induced seismicity? How can this be done optimally, both technically but legally? These are things that still have to be worked out. Those are, for me, the missed opportunities, but I think it's a question of time. We will have to come to a solution. How much shaking is acceptable and how much is dangerous? There are certain limits that have to be, let's say, defined, I would say, because, when you drive on your street with a car, you also create shaking to your house. It's not very strong. You don't even notice, but it's measurable. And that's why it's important that we define, what are acceptable limits of shaking, measurable limits. And, if this has been clarified and what happens if something happens, who's responsible, etc., I think then this can be overcome. It's a question of time.
All right.
Getting more questions and not less.
Yeah,
I have to speak faster.
Let's do a couple more before I close this meeting. So how long does a geothermal project take for completion? And in the case for deep geothermal?
It depends on when you define the start. If you define the start as when I ask my bank for financing, or when I start drawing up my plans, or do you mean when I start drilling the first well? Because sometimes the bureaucratic part takes longer than the actual technical part. Getting the license, getting all the funding, and meeting all the different requirements, legal requirements, etc. That can take quite long. But the actual drilling, you can drill 2 wells in a year is no problem. I think the fastest I've seen in the US was from first well drilling to actually operation in a geothermal power plant for electricity was 18 months. I was in Utah, but this is very fast.
All right.
Oh, Nevada, not in Nevada, not in Utah.
Let's do one more. Oh, sorry, were you going to say something else?
Oh no, I just corrected myself. That's all.
I noticed I skipped a question from Chung. Compared to biomass power plant or CHP, is geothermal energy more suitable for district heating system?
Well, it depends on the boundary conditions. I think in the Netherlands, I would say definitely yes, because for biomass, the amount of surface area that you need to grow the biomass is huge. So the surface footprint of biomass is bigger than for PV, right? Or for solar in general. And so biomass is great in a way, but in a densely populated area or country like the Netherlands, it will not play a major role unless you import it, right? And then, of course, there is this discussion, even with biomass, you have emissions. And, do you want these emissions? And what do you do about them? These are things that have to be taken into account. Geothermal really has virtually no emissions in the heating system, very low. And that's, so I think there it has a major advantage. That in terms of cost at the moment, biomass may have an advantage, depending on how good your geothermal reservoir is. But I think if you take all the impact, the environmental impact into account, and also the competition between food and biomass, I'm honestly not a great fan of biomass. For me, it's a niche technology in the Netherlands.
All right, so I think that will be the last question because of the time. Before we leave, I want to share a little bit about the Urban Energy Institute, because it's a research pillar from the TU Delft that deals with a lot of topics related to energy in urban. So if you like this lecture or want to learn more about this, you can scan the QR and go to the website to learn more about their projects and to also know more about their future presentations. We'll share a survey about this meeting, so please fill it in. At least they will send it in the chat and also in the emails. So you can have more information about future events, what you want to hear. And lastly, I want to thank you, David Bruhn, for giving this presentation. It was honestly very interesting and very happy to have you here.
Thanks for inviting me, Harvey. It was good.
The pleasure is ours. All right, then goodbye, everybody. Thank you for joining, and
Bye-bye.
See you in the next event.
Yes, and please don't forget to fill out the survey form. It really helps us for future events and all that. And this one includes a question about a possibility of an on-campus excursion when COVID is over. So let us know.
Thank you, everybody.
Thank you. Bye-bye.
Thank you.